These are notes for Chapter 10.3, Parametric Equations and Calculus. Okay, so we talked about parametric equations, and now we're going to talk about derivatives for parametric equations. So if a smooth curve C is given by the equation x equals f of t, with x being a function with respect to t, and y is g of t with respect to t, then the slope of C at the point xy is given by dy over dx is equal to basically y prime over x prime of t. So dy, we can think of this as dy over dt, and dx, we can think of this as dx over dt, where the denominator cannot be equal to 0. And so the first derivative I think is intuitive and it makes sense, but it's going to be the second derivative that takes a little bit of time to kind of get used to. So let's look at second derivative. d2y over dx2, we're essentially finding the derivative d of dx of dy over dx. So that makes sense, right? We want to find the derivative of this dy over dx. So let's expand this dy over dx. So dy, we can think of this as dy over dt, and dx, we can represent that as dx over dt. So now we have to think of this d over dx as impacting only this dy over dt. So if I put the d over dx of dy over dt, I can kind of rearrange and swap these denominators to end up with the rule that we have for the second derivative, which is d of dt of dy over dx all over dx dt. So this represents the second derivative for parametric equations. So we're basically finding the d over dt of dy dx. So dy dx is what we found from the first derivative all over dx dt. So I just wanted to highlight where this is coming from and the stages of changes that we take to arrive at the second derivative rule. So example 1, without a calculator, given that x equals 2 root t and y is equal to 3t squared minus 2t, find dy over dx, find the second derivative, and then evaluate at t is equal to 1. So we know that to find the derivative, we have to find y prime of t and x prime of t. So let's start first with x prime of t. To get to x prime of t, I'm going to first rewrite it with rational exponents. So rewrite this as 2t to the 1/2. If I want to find the derivative, I'm going to bring the 1/2 in front. 1/2 times 2 is 1, so that cancels out. Subtract 1 from the exponent, so 1/2 minus 1 is negative 1/2. So then here is my x prime of t. To find y prime of t, 3t squared becomes 6t, minus 2t becomes negative 2. So then we have y prime of t over x prime of t. So now this represents my first derivative, my dy over dx. And if I continue to simplify this t to the negative 1/2 is basically square root of t in the numerator. And if I take that numerator root t and distribute it through the parentheses, I'm going to get a dy over dx of 6t to the 3/2 minus 2t to the 1/2. So we found the first derivative. Now let's find the second derivative. So the second derivative, if we go back to our rule, is d of dt of dy over dx. So here's my dy over dx. So I'm going to find the derivative of this with respect to t all over dx dt. So my dx dt we found from the first derivative, which is t to the negative 1/2. Okay, so now once we have that in place, we're ready to find the derivative of dy over dx. So bring down the 3/2 in front. So 3/2 times 6 will give us 9. Subtract 1 from the exponent, going through power rule. So 3/2 minus 2 over 2 is 1/2. Go through power rule again. Bring down the 1/2. 1/2 times 2 is 1. Subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. All over my dx dt, which still remains there. So now we can simplify this even further. If I bring the t to the negative 1/2 up to the top, the t to the 1/2 times t to the 1/2 will just give me a t to the first power. And then the t to the negative 1/2 times t to the 1/2 will just cancel out to be just 1. So here's my second derivative, d2y over dx2. And finally, we need to evaluate both these derivatives at t is equal to 1. So here's my dy over dx. I'm going to evaluate this at 1, replace 1 in for t. So this is 1 to 3/2, which is 1. 1 to the 1/2 is 1. So 6 minus 2 will give me 4. And now d2y over dx2, my second derivative evaluated at 1, I simply plug 1 in for t. So 9 times 1 is 9. 9 minus 1 is 8. Okay, notice that the particle is moving at a velocity of 4 through, so this means that this is moving through a curved path because this dy over dx is moving faster, moving up than to the right. So it's moving up 4 times faster than it is moving to the right. And acceleration, this positive 8 indicates that this acceleration, this particle or this object is accelerating through this curved path at acceleration of 8. Okay, so now let's look at example 2. Again, without a calculator, given our parametric equations, being x equals 4 cosine t and y is equal to 3 sine of t, write an equation of the tangent line to the curve at the point where t is equal to 3 pi over 4. So, hey, don't overcomplicate things. Equation of the tangent line, all we need is an ordered pair and a slope. That's all we need. So to find the ordered pair, we need to find our x and y. So to find our x and y, well, we have our t value, 3 pi over 4. So if we plug this in, we can find out what the x and y values are. So plug in 3 pi over 4 for both t's, and cosine 3 pi over 4. This is going to be in the second quadrant. So cosine will be negative in the second quadrant. We have negative root 2 over 2. Multiply that by the coefficient, we get negative 2 root 2. Plug in 3 pi over 4 in for t for the y equation, and we get sine of 3 pi over 4. Sine in the second quadrant was going to be positive, so 3 times root 2 over 2 is 3 root 2 over 2. So here we have our ordered pair, negative 2 root 2 and 3 root 2 over 2. So we have our ordered pair. So now the only thing missing now is the slope. So to find the slope, we need to go through our formula, which is dy over dt over dx over dt. So, or another way to write it is y prime of t over x prime of t. So y prime of t, we need to find the derivative of y. So 3 sine of t turns into 3 cosine of t. For x prime of t, the derivative for 4 cosine of t, cosine becomes a negative sign. So x prime of t turns from 4 cosine of t into negative 4 sine of t. Now we need to evaluate our derivative at 3 pi over 4 so we can find our slope. So we're going to again plug 3 pi over 4 in for the t's here. So 3 cosine of 3 pi over 4. Well, actually what I did here was I just pulled the negative 3/4 out in front and then just evaluated the cosine over sine. So pull the negative 3/4 in front and then evaluate cosine of 3 pi over 4, which is negative 2 root 2 over 2. Sine of 3 pi over 4, which is root 2 over 2. Now these cancel out to be just negative 1. Negative 1 times negative 3/4 will give us positive 3/4. So here's our slope. We have our slope. We have our ordered pair. So now we just put this into our tangent line equation, which is y minus y sub 1 is equal to m times x minus x sub 1. And this should be negative 2 root 2. Just negative 2 root 2. Sorry, just positive 2 root 2. All right. Hey, let's continue with our notes with example 3. So example 3, without a calculator, find all the points of horizontal and vertical tangency given that x equals t squared plus t and y is equal to t squared minus 3t plus 5. So let's think about how we can find horizontal and vertical tangents. So horizontal tangent is where the numerator of our derivative is equal to 0. And vertical tangent could be potentially where our slope doesn't exist. So slope is not going to exist if the denominator of our derivative is equal to 0. Okay. So we simply have to set each derivative equal to 0 and to be able to identify them correctly. So our y prime, okay, our y prime will just be 2t minus 3, and the 5 goes away. So 2t minus 3, 5 goes to 0. And then x prime of t will be 2t plus 1. So the horizontal tangent is where our numerator of our derivative is equal to 0. So we simply set 2t minus 3 equal to 0, and we solve for t. We get t equals 3 halves. So horizontal tangent will occur where t is equal to 1.5. So we simply plug 3 halves back into our parametric equations to find our ordered pair. So without a calculator, we can just write everything out and no need to simplify. So this is my expression for to represent the x value, and this is the expression to represent the y value. Okay. Vertical tangent is going to occur where the denominator of our derivative is equal to 0, right? Where the slope does not exist. Horizontal tangent is where the slope is 0, so numerator of derivative is equal to 0. Vertical tangent is where the denominator of our derivative is equal to 0. So we set 2t plus 1 is equal to 0. Solve for t, we get t equals negative 1/2. So at t is equal to negative 1/2, we're getting an ordered pair that will create a vertical tangent. So we just plug negative 1/2 back into our parametric equations so we can get our x and y coordinate points. So plug negative 1/2 in for t squared plus t, which will give us negative 1/2 squared minus 1/2. And then we plug negative 1/2 into our y expression. Okay, parametric arc length. To lead into this, let's think about what we know about distance formula. So distance formula is simply going to be the square root of change of rate of delta x squared plus delta y squared, right? We're basically using Pythagorean theorem and solving for the hypotenuse. And then from there, let's recall the rectangular arc length. So rectangular arc length, we turn this into the square root of 1 plus f prime of x squared. Now, the way that we get from here to here is we divide both terms by delta x squared, which gives us 1, and then delta x over delta y squared. Delta x over delta y is the slope, or in other words, f prime. So we're basically finding these short segments, and we're taking these infinite short segments, and we are accumulating them all together to produce our rectangular arc length. So much in the same way, from rectangular arc length, we can get to our parametric arc length by finding the dx over dt plus dy over dt, and then squaring both of them, very much like how we go through the distance formula. And we're doing this in components where we're finding the rate of change of dx over dt plus dy over dt, and then we're adding these, accumulating all these segments with the definite integral from a to b. All right, so example 4, without a calculator, find the arc length of the given curve, x equals t squared, and y is equal to 4t cubed minus 1. All right, so let's find x prime of t, which we need. So t squared becomes 2t going through power rule. 4t cubed becomes 12t squared, and the negative 1 is a constant, so that will go to 0. Okay. All right, so now now we have our dx dt and our dy dt. We can just plug this into our parametric arc length equation formula. So we have our bounds from 0 to 1. So the definite integral from 0 to 1, the square root of x prime of t squared plus y prime of t, or dy over dt squared. Combine those together, we get 4t squared plus 144t to the fourth. From here, we can factor out greatest common factor, which is 4t squared, leaving us with 1 plus 36t squared inside the radical. And then this is a perfect square, so we can pull square root of 4 as 2 out, pull the t squared out as 2, and we could keep going here, because from here we can go through u substitution. We let the u value be this expression inside the radical, 1 plus 36t squared. We find the derivative. We go through u substitution to try and get this to be something that we can find the integral for, trying to get this to be a simpler problem. So 1 plus 36t squared, du over dt becomes 72t. Solve for dt, we get du over 72t. And we make our substitutions. The 2t will stay. Square root, this becomes u, and then dt gets replaced with du over 72t. Now we see the 2 and 72t are going to nicely cancel out, leaving us with just 2 over 72, which we can pull out as a coefficient of 1 over 36. And then we have u to the 1/2 du. So now we have a nice simple power rule that we can use. So u to the 1/2, we add 1 to the exponent. So this becomes 3/2. 1/2 plus 2 over 2 is 3/2, all over 3/2. Combine the 3/2 with 1 over 36. We can flip this to the numerator to be 2/3 times 1 over 36. And then convert the u back in terms of t. And now we can evaluate our upper and lower bounds. So plug 1 in for t, we get 37 to the 3/2. Plug in 0 in for t, we get 1 plus 0, so 1 to the 3/2. And then the coefficient 2/3 times 1 over 36 is 1 over 54. And this is not going to produce a nice number for us, but we do know that this is going to be positive length. And this is probably the exact value that we can provide. So our parametric arc length will be 1 over 54 times 37 to the 3/2 minus 1.